So what if I told you the electron doesn't, actually exist as a physical object?
Right, like a solid thing.
Exactly. Like, what if every fundamental particle making up your body, the chair you're sitting on, the device you're using to listen to this right now, what if literally none of it is fundamentally solid?
It's a huge shift in how we see things.
It really is. What if reality, at its absolute deepest level, is just a complex three-dimensional shadow cast by pure geometry?
Welcome to the Deep Dive. Today, we are attempting to completely rebuild your understanding of the physical universe.
And it is a profound shift in perspective. I mean, we are so accustomed to thinking of the universe as just this collection of things, right? Things with mass, things with charge.
Yeah, little tiny billiard balls bouncing around.
Exactly. But to truly engage with the material we have on the table today, you kind of have to let go of that deeply ingrained materialist assumption.
Right, you have to toss it out. And if you're someone who follows physics, you know that our current rule book, the standard model of particle physics, has essentially stalled out.
It's hit a wall. It has. For decades, it's been the undisputed champion of science. It predicts things to incredible decimal places. But if you actually talk to theoretical physicists behind closed doors, there is this pervasive sense of, well, frustration.
Oh, absolute frustration.
Because the standard model is an incredibly messy spreadsheet. It relies on something like 26 arbitrary fundamental constants.
And that is the core of the modern crisis in physics, really.
Yeah.
We have to manually measure the mass of a top quark or, the exact strength of the electromagnetic force, and we just physically type those numbers into our equations to make them work.
Right, there's no deeper why.
Exactly. The standard model cannot tell you why an electron weighs what it does. It just shrugs and says, that's just how the universe is.
Just trust us.
Yeah. And to mathematically survive the chaotic subatomic world, traditional physics relies on quantum electrodynamics, or QED, which uses continuous quantum fields, seas of virtual particles bubbling in and out of existence, and this mathematical technique called renormalization.
Renormalization, which,
Oh.
let's be honest, is a very fancy word for sweeping infinite universe-breaking numbers under a mathematical rug so the equations don't explode.
It is a bit of a mathematical sleight of hand.
Even the founders of QED, like Richard Feynman, felt deeply uncomfortable with it. It just feels like a hack.
It does. It feels like we are adding epicycles to planetary orbits,
Right.
like making a flawed system more and more complicated just to keep it functioning, rather than finding the elegant truth underneath.
Which is exactly the frustration that sets the stage for the paper we are diving into today. It's titled Trans-Dimensional Unified Field Theory V3.
By George James Dukas.
Right. And we'll just call it TDUFT for the rest of this discussion to keep it simple. And our mission today is not to just read you abstract math. Our goal is to guide you through a framework that claims to throw out the virtual particles, throw out the arbitrary tuned parameters, and replace them with a single logical geometric structure.
It's incredibly ambitious.
It really is. The paper argues that everything, charge, mass, spin, and even particle instability arises from the discrete orientation of what the author calls a D-ladder.
The D ladder. And this is the central architecture of this entire theory. So instead of imagining reality as a soup of continuous fluctuating fields, TDUFT models reality as a rigid sequence of dimensional tiers.
Like rungs on a ladder.
Exactly. And the fundamental interactions we observe, like electricity and gravity, are just geometric projections moving up and down this ladder. So if we want to understand how this universe is built, we have to start at the foundational rung, a level the paper designates as tier D squared.
Tier D squared, the charge tier. So this is where the property we casually call electrical charge actually originates, but it doesn't come from a field, and it's not an intrinsic magical property.
No, it comes from three distinct directional axes.
Okay, let's unpack this concept of the charge triad because it requires a complete conceptual reset.
It really does. In traditional physics, if you ask a professor why an electron has a negative charge, they'll just tell you it's an intrinsic property. It just does. It's a given.
End of story.
Right. But TDUFT vehemently rejects that. It states that charge is a strictly emergent property.
It's an output.
Yes, every particle's charge is exclusively determined by how it aligns across three spatial axes at this D squared tier.
So the particle doesn't, possess charge. It possesses a specific physical orientation, and charge is just the byproduct of that orientation.
Exactly.
So let's actually look at these three axes because they form the geometry of everything else we're going to talk about today. The paper defines them very specifically. First, you have the spin director.
Denoted as S sub.
Right, which governs rotational alignment.
Yeah.
Second, there's dimensional polarity, D plus minus, which dictates the branch direction. So essentially whether the geometry favors a positive or negative structural branch.
Correct.
And third, the vibration direction, V dear, representing the axial orientation.
And what you need to picture here is a discrete coordinate system. What makes TDUFT so radically different from quantum field theory is its reliance on discrete binary-like states.
Right, no infinite fuzziness.
Exactly. A continuous field can fluctuate to any infinite degree. But these three axes operate almost like mechanical switches. For each axis, spin, polarity, and vibration, a state can only do one of three things.
Okay.
It can perfectly align with the dimensional branch, it can perfectly anti-align, or it can sit perfectly neutral, meaning it is orthogonal, or at a 90-degree right angle to the branch.
You know, when I was reading this section, the image that immediately jumped into my head was a combination lock, like the classic three-dial padlocks on a high school locker.
That's a great analogy.
Right, because imagine that clicking the dials doesn't open a door, but instead the combination you dial in actually manifests a particle into observable reality.
I like that.
So you take the first dial, the spin director, and you click it into alignment. Then you click the dimensional polarity dial into place. Then the vibration direction dial. The specific combination of those three mechanical clicks generates what we perceive as charge.
The combination lock is a highly effective way to visualize this. What is the defining feature of a dial lock? It clicks into a discrete slot.
It doesn't hover between a 3 and a 4.
Exactly. It doesn't hover seamlessly. If the underlying spatial geometry dictates that alignment must snap into specific orthogonal states, then the output, the physical property generated by that alignment, must also be strictly discrete.
And if you're listening and putting the pieces together, you'll realize this combination lock geometry directly attacks one of the deepest, most stubborn mysteries in the history of physics: the quantization of charge.
The mystery of why charge, always, without exception, arrives in neat little mathematical fractions.
Yes, because if you go back over a century to the famous Millikan oil drop experiment, we discovered that electrical charge isn't a smooth, continuous fluid. It is fundamentally chunky.
Very chunky.
You look at the real world, and you never, ever find a particle floating around with a charge of like 0.73 or 0.11.
No.
It's always strictly regulated. An electron is -1. A proton is +1. And when we eventually discovered quarks, they were always +2/3 or -1/3. It's always thirds.
Always.
But standard physics has absolutely no mechanism for why it's thirds.
Right. The standard model treats the fractional charge of quarks as just an empirical input. We observed it in deep inelastic scattering experiments, so we wrote it down in the textbooks.
We just accepted it.
Yeah. But there is no foundational law in QED that strictly forbids a particle from having a charge of 1/5 or 1/7. It is merely an observed rule.
But in TDUFT, the mystery of the thirds isn't a mystery at all. It is a mandatory structural consequence of 3D space, because the d-squared charge tier is constructed from exactly 3 directional dials. So the math required to calculate fractional charge goes from incredibly abstract to something you can do on a bar napkin.
It literally transforms into a counting exercise.
Yeah.
The paper lays out a unified QED formula for charge. It states that charge, represented by Q, is equal to the sign dictated by the polarity axis, multiplied by the number of aligned axes, divided by 3.
So n aligned over 3.
Exactly. N aligned over 3.
That is the entire formula for universal charge. So let's take that and actually walk through the particle zoo, because the elegance of this is striking.
Let's do it.
Let's start with the electron, or its antimatter twin, the positron. According to the paper, an electron represents a state where all 3 axes, spin, polarity, and vibration, are fully clicked into alignment with the dimensional branch. So your n-aligned value is 3.
And if you plug that into the formula, 3 aligned axes divided by a total of 3 axes equals 1.
A full whole number charge.
The electron's charge is solved by pure geometry.
Now let's look at the quarks, the building blocks that make up the protons and neutrons in our bodies. In traditional physics, an up quark has a positive 2/3 charge. If we apply the Duquesne geometry, what is an up quark?
Geometrically, an up quark is simply a state where only 2 of the 3 axes have clicked into alignment.
Okay.
The third axis is just sitting neutral, orthogonal to the branch. So your n-aligned value is 2. You divide that by the 3 total axes, and you get exactly 2/3.
Wow. And the down quark, which has a negative one-third charge?
Just one axis aligned, two sitting neutral, and aligned is 1. 1 divided by 3 is 1/3.
And a photon, the fundamental particle of light that carries the electromagnetic force, but famously has strictly zero electrical charge.
A photon represents a state with 0 axes aligned to the charge branches. And aligned is 0. 0 divided by 3 is 0.
It's perfectly neutral.
Completely orthogonal to the d² charge structure.
Okay, but I have to push back here for a second because this sounds almost too clean. In standard physics, quarks are fundamentally different beasts from electrons, right? They experience the strong nuclear force, they carry colored charge, they are confined inside protons. TDUFT seems to be implying that quarks aren't these bizarre, fundamentally distinct entities. They're just, well, are they just lazier electrons?
Lazier electrons, right.
Like they're just geometric states that failed to click all three dials into place. How does that reconcile with decades of particle physics?
It is a massive conceptual friction point. You're right to point that out. But TDUFT doesn't deny the empirical behavior of quarks. It fundamentally recategorizes their origin.
Okay.
In this framework, a quark is not a fractured piece of fundamental matter. It is a partial dimensional projection. The reason charge is quantized into thirds is inescapable. You literally cannot have half of a spatial axis.
Right, it's binary.
An axis is either aligned or it isn't. The discreteness of charge is an unavoidable physical consequence of living in a universe built on a 3D structural orientation. You asked how this reconciles with standard physics. The author argues it doesn't have to reconcile with the narrative of standard physics.
It just has to match the data.
Exactly. It only has to flawlessly reproduce the data. And this geometric projection reproduces the fractional charge data flawlessly without requiring infinite fields or renormalization.
It grounds an abstract, almost mystical property electrical charge into cold, hard spatial mechanics.
It really does.
But calculating charge is just the opening act of this paper, because once we understand that these axes exist and have to align, we run into a physical inevitability, right? Anytime you have alignment, you create a bias.
You do.
You create an imbalance in the system. And this brings us to one of the most critical and, frankly, easily misunderstood concepts in the entire TDUFT framework, entropy.
Yes, and we really need to establish a very strict definition here because the word entropy carries a lot of baggage for anyone who has taken a thermodynamics class.
Exactly, because when I hear the word entropy, my brain immediately goes to the second law of thermodynamics. I think of a hot cup of coffee cooling down or, my office getting messier over time.
Right.
Or the ultimate heat death of the universe. It means chaos, disorder, the loss of usable energy. But as I was reading this section of the paper, I realized Dukas is talking about something completely different, isn't he?
He is using the term in a purely structural, dimensional sense. It has nothing to do with thermodynamic heat loss.
Okay.
In TDUFT, entropy means dimensional imbalance. Specifically, it is the fundamental imbalance between two opposing magnitudes on the D ladder, expansion and contraction.
Expansion, contraction of what, exactly? Space itself.
Of the underlying dimensional metric. The paper argues that reality is suspended in a constant tension. It assigns a positive, destabilizing outward magnitude to the expansion branch, which is labeled with the Greek letter phi.
Phi, got it.
And it assigns a negative, stabilizing inward magnitude to the contraction branch, labeled psi. So when particles' three axes align to create charge, they aren't just passively sitting there. That alignment heavily favors one side of this fundamental tension.
It leans.
Exactly. The triad geometry at the d² tier collapses into a specific mathematical ratio of these two magnitudes.
Yeah.
Phi over Ci, expansion over contraction.
So the geometry forces a structural bias. The architecture is physically leaning. And the paper explicitly defines this specific ratio of phi over psi as the entropy of the charge tier.
Correct. And this isn't just an abstract philosophical point. The author takes this exact entropy ratio and uses it to systematically solve the most famous numbers in quantum mechanics.
This is where it gets crazy.
He starts with the crown jewel of physics mysteries, the fine structure constant known as alpha.
Now, if you are listening to this and you aren't familiar with alpha, it is impossible to overstate its importance. Alpha is roughly 1 over 137.
1 over 137.035999, it goes on. It is a dimensionless number, meaning it has no units like meters or seconds attached to it. It's just a pure number.
And it dictates the strength of the electromagnetic interaction. It determines how tightly electrons are bound to the nucleus of an atom. Richard Feynman, who we mentioned earlier, famously called alpha one of the greatest damn mysteries of physics.
He did.
He wrote that it's a magic number that comes to us with no understanding by man, as if the hand of God wrote that number and we don't know how he pushed his pencil.
It's poetry, really.
It is. Physicists have spent entire careers trying to logically derive why alpha is exactly 1 over 137 instead of just measuring it in a lab.
Because the stakes are existential. If alpha were even slightly larger or smaller by a fraction of a percent, the delicate fusion processes inside stars wouldn't work. Carbon wouldn't form. Life, as we comprehend it, would be physically impossible.
Wow.
The standard model treats alpha as a fundamental input, a tuned parameter. But TDUFT claims to mathematically derive the exact value of alpha using nothing but this dimensional entropy ratio.
The derivation in the paper is staggering because of how visually simple it is. The theory states that if you take this entropy ratio phi over Ci and you apply a geometric 360-degree gate to it, you get alpha.
Let's unpack the mechanics of that 360-degree gate, because that is where the physics actually happens. Why 360?
Right. My first thought was, okay, 360 degrees in a circle, but how does drawing a circle create a fundamental constant of the universe?
In TDUFT, a particle is not static. Its existence on the D ladder is modeled as a continuous cyclic progression. To manifest a measurable property into our observable universe, the dimensional geometry must complete a full cycle of orientation across its axis.
Like a full rotation.
That is a full 360-degree rotation in the abstract geometric space. So by multiplying the internal entropy ratio, the phi over psi imbalance, by 360, the theory is essentially translating an internal hidden structural tension into an outward observable coupling constant.
So the equation is literally just alpha equals the entropy ratio, phi over c psi, multiplied by 360. That single line of math replaces decades of hand-wringing over where this magic number comes from. It's not magic. It's the geometric output of a full rotation acting on the expansion-contraction imbalance of the universe.
It radically redefines what a fundamental constant actually is.
Yeah.
It totally removes the mysticism.
But if this entropy ratio, this phi over psi tension, is truly the universal gear driving electromagnetic physics, it can't just be a one-trick pony.
Right. It has to do more.
It can't just solve alpha and call it a day. It has to explain other quantum behaviors.
And the paper immediately applies it to the next major hurdle in QED, the electron spin response, known as the G factor, or the anomalous magnetic dipole moment.
This is a great test case because the G factor is one of the most rigorously tested numbers in human history. To give you some context, back in the 1920s, Paul Dirac wrote down an equation for the electron that is still one of the most beautiful pieces of math ever conceived.
It's legendary.
Dirac's math predicted that the electron's spin G factor should be exactly 2, a perfect integer. But years later, experiments got better, and we realized the electron was wobbling just a tiny bit more than Dirac predicted. The actual G factor isn't 2, it's roughly 2.00002319.
And that tiny extra wobble, the 0.002319, is the anomaly. And explaining that anomaly is what earned Julian Schwinger, Shinichiro Tominaga, and Richard Feynman their Nobel Prizes.
Right.
Traditional QED explains that wobble by arguing that the electron is constantly emitting and reabsorbing a cloud of virtual photons. And those virtual photons are emitting virtual electron-positron pairs. It's an infinite nesting doll of virtual particle interactions.
Which sounds exhausting.
It is. To calculate the G factor to its current precision in the standard model, physicists have to calculate thousands and thousands of intensely complex Feynman diagrams, summing up all these infinite virtual interactions.
Thousands of diagrams, supercomputers running for months just to figure out why an electron wobbles a fraction of a percent more than it should. But Dukas steps in with TDUFT and says, you don't need a cloud of virtual ghosts to explain the wobble. The electron is simply responding to its own geometric entropy. It's fighting the phi over psi imbalance.
And the math the paper presents for the G factor is remarkably elegant. It posits that you start with Dirac's base spin of 2. That is the perfect baseline.
Okay.
Then you calculate the deviation by adding the specific geometric orientation of the particle. We established earlier that an electron has an alignment fraction of 3 over 3, which is 1. You take that alignment fraction and you simply multiply it by the universal entropy ratio, phi over psi.
So the TDUFT equation for the electron's G factor is simply G equals 2 plus the alignment fraction, which is 1 times phi over Ci.
Exactly.
And when you plug in the exact value of phi over psi that was just derived from the fine structure constant, well, sorry, not ellipsis, but when you run the numbers, the math spits out 2.002319.
It perfectly hits the empirical anomaly without calculating a single Feynman diagram.
This was the moment in the paper where I actually had to stop reading and walk away from my desk for a minute.
It's a lot to take in.
It is. Let's really absorb what this implies. If this math holds up, it means the fine structure, constant, the magic number of the cosmos, and the anomalous magnetic wobble of an electron are not separate, isolated physical phenomena requiring different mechanisms to explain.
No, they are structural cousins.
They are fundamentally the exact same thing, just observed from different angles.
The entropy ratio is the universal weight applied to the particle's orientation. The standard model treats them as distinct properties requiring separate, incredibly complex calculations. But TDUFT shows that the 360-degree rotation of the entropy gives you alpha, and the linear addition of that exact same entropy to the base spin gives you the G factor.
Wow.
It is a stunning display of geometric unification.
It really strips away all the mathematical noise. But as paradigm shifting as this is for charge and spin, we still haven't tackled the absolute behemoth of modern physics. We haven't talked about mass.
That.
We've built an electron that has a negative charge and spins with a specific wobble. But why does that electron have physical weight? Why does it possess inertia? Why does it resist being pushed?
This is where the theory moves into profound ontological territory. To understand mass, we have to leave the d-squared charge tier. We have to climb one rung higher on the d ladder, moving into tier d cubed.
Which the paper defines as the volume and voltage tier.
Yes.
Now, the paper uses an analogy here that I want to explore, but I also want to refine it because it can be tricky. Dukas talks about the mass shadow.
The mass shed.
The idea is that an electron doesn't actually exist natively on the d-cubed mass tier. It lives down on the d-squared charge tier. But because of its specific geometrical orientation, the way those three dials are locked into place, it casts a dimensional shadow upward onto the d-cubed tier. And we, as observers in a macro universe, perceive that d-cubed shadow as physical mass.
The term shadow is evocative, but you are right to be cautious, because an optical shadow like the one you cast on a sidewalk on a sunny day has no weight. It possesses no inertia. If we are trying to explain why matter has mass, we have to explain where the resistance to acceleration comes from.
Exactly. So instead of a visual shadow on concrete, I want you to imagine a volumetric displacement. Think of dragging a complex, rigidly locked shape through a thick fluid. Or think of a rapidly spinning gyroscope.
A gyroscope is perfect.
A gyroscope resists being tipped over. It fights back against your hand. Why? Not because it suddenly gained more stuff inside of it, but because its spatial geometry and its momentum are locked into a specific configuration that violently opposes a change in orientation.
That is a much more accurate physical visualization of the d-ladder mechanics. Mass is not an isolated, standalone property. An electron does not have a tiny little pool of mass fluid inside it.
Right.
Mass is the geometric resistance generated when a fully aligned d-squared triad projects its orientation into the three-dimensional volume of the d-cubed tier. It is dimensional inertia.
Let's look at the mathematical formula Dukas uses to describe this volumetric shadow. The base geometric mass formula in the paper is mass equals the d-cubed operator multiplied by the time operator squared. So m equals d cubed times t squared.
Right.
But wait, why time squared? We're talking about spatial geometry and shadows. What is the time operator doing in a mass equation?
It is the mechanism that locks the geometry into observable reality. A purely spatial geometry, frozen in an instantaneous snapshot, has no mass. It is just an abstract coordinate system.
Okay.
For that geometry to express physical inertia, for it to push back against a force it must endure, it must evolve through time. The t-squared operator essentially represents the persistent duration of this specific geometric configuration. It anchors the 3D volume, giving it a stable presence that we measure as mass.
Okay, so mass is the d-cubed volume enduring through time squared. But the actual character of that mass, its specific weight, is entirely dictated by the entropy we just spent so much time discussing. The shadow takes the shape of whatever is casting it.
Precisely. The unified mass identity in TDUFT dictates that you can calculate the electron's mass by taking that base d-cubed volumetric operator and modifying it with the exact same variables we use for the G factor.
Oh, this is cool.
You multiply the d-cubed operator by the electron's alignment fraction, which is 3/3, or 1, and then multiply it by the universal entropy ratio, phi over Ci.
So the equation is mass equals d cubed times n aligned over 3 times phi over Ci.
Yes.
This is beautiful because it's the exact same mathematical skeleton we use for spin, just applied to a volume operator instead of a spin operator. But here's the major question I had reading this. We are manipulating pure geometry. How do we extract actual real-world physical units from this?
That's the million-dollar question.
Because an electron doesn't weigh 1 phi over psi, it weighs exactly 0.511 mega electron volts, or MeV. How does pure math cross over into 0.511 MeV?
It crosses over through a necessary process of dimensional normalization. This is a critical point to grasp. Physical units like kilograms or electron volts, they're human inventions.
We just made them up.
We did. They're arbitrary scales we created to measure the universe relative to ourselves. A theory of pure geometry cannot derive a kilogram out of thin air. Instead, what TDUFT does and what all of physics does, frankly, is set an anchor point.
Like how general relativity anchors its math to the empirical gravitational constant, big G.
Exactly. TDUFT normalizes the underlying d-cubed operator to the electron. The electron represents a perfect primary first-order triad alignment. It is the cleanest mass shadow in the universe.
Okay.
So the theory essentially says we will define the scale of the d-cubed operator such that a fully aligned triad shadow corresponds to a measured value of 0.511 MeV.
We lock the fundamental scale to the electron. We calibrate the geometric machine.
Right.
But once you set that anchor, the true test of the theory begins. If this d-Lato framework is real and not just a clever mathematical trick tailored for the electron, it must be able to predict the rest of the universe based solely on that single calibrated anchor. If the scale is set, the math has to work for everything else.
And that leads directly to a massive apparent collision with reality. Because the moment you step past the electron and look at its heavier cousins in the standard model, the clean, simple geometry seems to completely break down.
Let's talk about the misfits of the particle zoo. The muon and the tau particle. If you don't know what these are, just think of them as fat, highly unstable clones of the electron.
Good description.
They have the exact same negative charge as an electron. They have the exact same spin as an electron, but their mass is wildly different. The muon weighs about 105 MeV, which is roughly 200 times heavier than an electron.
Significantly heavier.
And the tau particle is a staggering 1776 MeV, over 3,000 times heavier. In standard physics, nobody knows why. We just measure them and accept it.
But in TDUFT, we have strict rules. We have an alignment fraction and aligned over 3. So the immediate logical assumption is to try and plug different alignments into the mass formula.
Right. If the electron has 3 out of 3 axes perfectly aligned, maybe the heavier, unstable muon only has 2 axes aligned, and the super unstable tau only has 1 axis aligned. So I play the skeptic, I take the TDUFT mass formula, and I plug in n equals 2 for the muon. The formula spits out a mass of 0.34 MeV.
Which is an abysmal failure, considering it needs to be 105 MeV.
And if I plug in n equals 1 for the tau particle, the math gives me 0.17 MeV, which is hilariously wrong. It needs to be nearly 1800 MeV.
Okay.
So I hit this section of the paper and I thought, well, it's over. The theory is fundamentally busted.
It seems that way at first glance.
The geometry works perfectly for the electron and then completely fails the moment you test it on the muon. How does Dukas salvage this?
He anticipates this exact failure, because the error is in our assumption. We assume that the muon and tau are simply misaligned electrons. We assume they reside on the same primary geometric plane as the electron.
And they don't.
They don't. TDUFT argues that the muon and tau are not base states. They are higher-order structural projections.
Higher order projections. I struggled with this until I started thinking about it like acoustic resonance, like an audio feedback loop.
Explain that.
Well, if you stand in a canyon and shout, the first echo that bounces back to you is the loudest and clearest. That primary echo is the electron. It is the first stable shadow cast directly from d squared to d cubed.
Okay, I see where you're going.
But the sound doesn't stop. It hits another wall and bounces again. That second echo is warped, heavily distorted, and carries different acoustic energy. That second order bounce is the muon. And the third bounce, which is incredibly chaotic and resonant, is the tau.
The resonance analogy is incredibly apt, because mathematically, how do you handle complex, resonating, interacting feedback loops? You use matrices. Dukas addresses the heavy leptons by introducing what he calls the quatus and a closed-loop eigenstructure.
Okay, let's break down those terms, because closed-loop eigenstructure sounds like impenetrable jargon. What is a matrix doing in this physical geometry?
In linear algebra, a matrix is simply a grid of numbers that describes a transformation, how a space stretches, rotates, or in this case, reverberates across dimensional tiers.
Okay.
The D-ladder is not a one-way street. When a triad casts a mass shadow, that spatial distortion creates a feedback loop, a closed loop. The eigenvalues of this matrix are simply the natural resonant frequencies of that geometric feedback loop.
So it's like a guitar string.
Exactly. Just like a guitar string can only vibrate at specific harmonic frequencies, the dimensional space can only hold mass at specific resonant eigenvalues.
So you don't just manually guess that the muon has an n value of 2.
Yeah.
The alignment order, the actual structural identity of the muon, is dynamically calculated by solving the natural resonance of this closed-loop matrix.
Yes.
The muon isn't physically missing an axis. Its effective geometric alignment is shifted because it is a higher-order harmonic of the electron's mass shadow.
And what is profoundly fascinating here is the direct parallel to traditional quantum electrodynamics. We discussed earlier how QED uses renormalization and calculates thousands of Feynman loop diagrams, particles, interacting with their own virtual emissions to find the true mass of a heavy particle.
The radiative corrections.
Right. TDUFT essentially claims that those virtual particle loops are just a complicated, messy way of describing geometric resonance. The closed-loop matrix achieves the exact same structural hierarchy as QED's infinite diagrams, but it does it cleanly, through the strict eigenvalues of the spatial geometry itself.
It's like finding a secret backdoor into the code of reality. It acknowledges that the muon and tau are vastly more complex than the electron without having to invent any new fundamental forces to explain them. They are just heavier, unstable echoes of the exact same geometric operator.
But the introduction of these unstable higher-order echoes serves as the preamble for what is arguably the most audacious, paradigm-shattering section of the entire manuscript.
Oh yeah, this next part is wild.
Because once Dukas establishes that some particles sit off the primary boundary, that they are unstable resonances, he formulates a universal mathematical law to govern every unstable particle in existence.
Section 6. The Universal Unstable State Mass Law. I read the section 3 times because the claims are so massive.
They are.
The Standard Model treats the masses of the heaviest particles, the top quark, the W and Z bosons, as totally disconnected mysteries. They are chaotic. But TDUFT claims to have found a single equation that perfectly weighs all of them. To do this, the paper draws a hard, defining line across the particle zoo.
It creates a strict dichotomy. On one side, you have boundary particles. These are particles like the electron, the muon, or the pion. Even though the muon requires a higher-order matrix to find its specific tier, it still cleanly fits the base 3D dimensional mass law. It is geometrically stable within its volumetric boundary.
Okay, that's one side.
But on the other side of the line, you have unstable particles. The tau, the top quark, the W and Z bosons. These particles violate the clean 3D rule. They are overwhelmingly massive, and they fall apart in fractions of a trillionth of a second. They sit entirely outside the stable dimensional boundary.
They are the ultimate misfits, and to mathematically handle them, the author unveils a new formula. It looks a little intimidating at first, but we are going to break it down piece by piece, because the underlying logic is brilliant. The universal unstable mass equation is m sub n equals lambda 1d multiplied by m sub 0 minus k sub u times f of d.
Let's translate that.
Yeah, let me translate that into English. The final observable mass of the heavy particle is equal to a one-dimensional projection factor multiplied by the base tier mass minus an entropy tax.
Let's unpack the two new mechanisms here, starting with the lambda 1d term, the one-dimensional projection. This is a profound geometric concept. The theory argues that because these particles are so incredibly unstable, their dimensional geometry is failing.
It's breaking down.
Right. It cannot maintain the stable, volumetric 3D shadow required for normal mass. Instead, the geometry is forcefully collapsed or projected down into a single mathematical dimension.
It's losing its depth. It's being flattened by its own instability. But how does that affect the mass calculation? The paper states that the numerical value for this lambda 1d projection factor is exactly 10. It is a literal decimal shift. Why 10? How does collapsing a 3D volume into a 1D line give you a clean multiplier of 10?
It relates to the fundamental scaling limits of the dimensional framework itself. In the architecture of the D ladder, mapping a higher dimensional volumetric state down onto a singular 1D coordinate line forces a maximum structural scaling.
Okay.
The mathematics of the geometry dictate that this dimensional flattening acts as a tenfold amplifier of the base mass magnitude. It takes the internal dimensional scale, which would normally express as a light 3D volume, and forces it through a 1D lens, scaling it up by a factor of 10 to shove it into our observable mass band.
It's a multiplier effect caused by dimensional collapse. So you take the base tier mass and multiply it by 10. But then you have the second half of the equation minus k sub u times f of d. The entropy tax. This might be my favorite concept in modern physics.
It is remarkably intuitive. The framework argues that existence is not free.
Nothing is free.
Right. Because these particles are so incredibly short-lived, because they are violently rushing toward decay and structural disorder, there's an energetic cost to their manifestation, an instability tax. The universe essentially deducts a specific amount of mass to account for the chaotic, unbalanced nature of the particle's geometry.
It's literally the universe auditing a particle, like, oh, you're only going to exist for a millionth of a picosecond before exploding into lower-tier radiation. We are taking a cut of your projected mass.
That's exactly it.
And a tax is just an abstract idea until you can actually calculate it. The genius of the paper is how it uses the tau particle to strictly calibrate this universal tax rate.
The tau calibration anchors the entire high-mass unstable spectrum. Let's look at the hard numbers. We know from decades of experimental collision data that the tau mass is roughly 1776.8 MeV.
Yeah.
We know that as a cold empirical fact.
Right.
TDUFT calculates that the theoretical base dimensional mass for the tau's specific tier, that m sub 0 value before the projection and the tax, is 210.8 MeV.
Okay, let's run the universal law together. We take the base mass of 210.8 and we apply the 1D projection. We multiply it by 10. That gives us a projected mass of 201.08 MeV.
But the real-world tau mass is only 1776.8. It's significantly lighter than the 1D projection predicts.
Exactly. So to find the exact value of the entropy tax, we just subtract the real mass from the projected mass. 2108 minus 1776.8 gives us exactly 331.2 MeV.
That value, 331.2 MeV, is the absolute magnitude of the entropy tax for the high unstable mass band. That is the chunk of mass burned away by the particle's shear instability.
And this right here is where the paper transforms from a curious alternative theory into something that demands serious attention. We just locked in the rules. The 1D projection is a 10x multiplier. The entropy tax is 331.2 MeV. What happens if we take this exact same law, no tweaks, no new tuned parameters, no invented forces, and apply it to the heaviest, most bizarre fundamental particle known to science? The top quark.
The top quark is an absolute monster. It was discovered in 1995 and it shocked physicists because it is insanely heavy. Experimentally, it weighs in at about 172.5 giga-electron volts. It is roughly 175 times heavier than an entire proton.
It's massive.
It sits completely isolated, wildly outside the mass band of normal fundamental particles.
So we go to the TDUFT closed loop matrix to find the base tier for the top quark. The underlying geometry calculates a starting base mass of 17.25 GeV. We apply the universal law. We multiply the base mass by the 10 by 1D projection factor. 17.25 times 10 is 172.5 GeV.
And then you calculate the entropy tax.
Right, but because the top quark sits at the absolute uppermost boundary limit of this unstable band, it is the ceiling of the D-ladder structure. Its relative entropy tax term approaches 0. So the final predicted mass is exactly 172.5 GeV.
It perfectly hits the real-world weight of the top quark. Dead on.
It's crazy, but the author keeps going. Let's look at the W boson. In the standard model, this is the particle responsible for the weak nuclear force radioactive decay. The real-world measured mass of the W boson is 80.37 GeV. What is the TDUFT base tier mass? 8.037 multiplied by the 1D projection of 10, 80.37 GeV.
And the Z boson, the neutral partner to the W real-world mass, is 91.19 GeV. TDUFT base tier mass is 9.111 multiplied by 10, 91.19 GeV.
It is flawless.
Yeah.
A single mathematical structure-based geometric tier multiplied by 10 minus an entropy tax perfectly derives the mass of the tau, the top quark, the W boson, and the Z boson. And the paper even spends time showing how this exact framework scales down to the lower unstable band.
Right, particles like kaons, eta mesons, d mesons.
Exactly. The 10x projection still applies, but the entropy tax operates on a sliding mathematical scale based on their specific tier position, and it predicts all of their masses beautifully.
If you pause and truly consider the historical context of what we are discussing, it is a staggering theoretical achievement. In standard quantum field theory, the masses of the top quark, the W and the Z, are completely separate mysteries.
They don't relate to each other.
No, they don't. The W and Z bosons get their mass through a highly specific interaction with the Higgs field, known as electroweak symmetry breaking. But the top quark gets its mass from a completely different coupling strength to the Higgs field.
Right.
There is no underlying reason why the top quark's coupling is so vastly different from an up quark's coupling. They're unrelated, arbitrary numbers. But TDUFT reveals that they are not unrelated at all. They all sit on the exact same universal geometric line. They are all just one-dimensional projections of base spatial tiers.
It's like finding a Rosetta Stone for particle mass. It proves that the universe isn't just making up chaotic new rules and generating random constants every time a new heavy particle is manifested. There is a single underlying geometric code. Which brings us to the final grand synthesis of the paper. Because over the course of this deep dive, if you've been tracking closely, you'll realize we've actually presented three completely different ways to calculate mass.
We have. And to a critical listener, it might seem highly contradictory. We started our discussion of mass with the pure geometric equation, m equals d cubed times t squared, the pure 3D volumetric projection of the charge triad through time.
Right, but then there's another expression used earlier in the paper known as the charge gravity expression. Mass equals c cubed times t over g, where c represents the charge orientation magnitude and g represents the geometric entropy leakage factor.
And finally, we just spent the last 20 minutes exploring the unstable projection law. Mass equals lambda 1d times the base mass minus the entropy tax. Three different mathematical expressions for mass.
It sounds messy.
But in the final section of the paper, the author brings all three of these expressions together in a massive 3x3 grand matrix to prove that they are not competing theories. They are mathematically identical.
This is where the entire theory clicks together like a vault door locking. Let's unpack this grand matrix. These aren't three separate mechanisms for mass. They are simply three different mathematical lenses looking at the exact same geometric operator, just applied under different physical contexts.
Precisely. Let's break the lenses down. The geometric formula, d cubed t squared, is the full, unadulterated foundation. It is the raw, pure 3D volumetric shadow. It is mass viewed strictly through the lens of spatial dimension.
Then you have the charge gravity formula, c cubed t over g.
Right. This is the exact same underlying geometry, but rewritten to explicitly show cause and effect. It shows how the specific orientation of the charge acts as the c variable directly interacts with the entropy leakage, the g variable, to create that mass.
Okay, I follow.
The paper rigorously, mathematically proves that d cubed t squared and c cubed t over g equate to the exact same value, same shadow, just viewed through the lens of charge orientation rather than pure volume.
And then the third lens, the unstable projection formula.
Yeah.
That's just taking that exact same base mass, the d cubed volume, and acknowledging that the particle is too unstable to hold its 3D shape. So it gets projected down into a one-dimensional line, which triggers the 10x multiplier, and then it pays the entropy leakage tax, which is literally just the localized expression of the g variable from the second formula.
What is truly fascinating here is the sheer inescapable structural rigidity of the theory. Think about the symmetry. You have three directional axes of orientation: spin, polarity, and vibration. You have three expressions of mass: geometric, charge gravity, and unstable projection. And you have three fundamental categories of particles: stable interior particles, stable boundary particles, and unstable off-boundary particles. Every single particle category, every mass identity, every projection law, they all seamlessly emerge from one single operator acting across the rungs of the D ladder.
The paradigm shift. That is the core takeaway for you listening today. What George James Dukas has presented in the TDUFT framework is a claim of absolute sweeping unification. He has unified electrical charge, physical mass, quantum spin, and the chaotic instability of heavy particles without inventing a single new fundamental force.
None.
No Higgs field is required to give particles mass. No strong nuclear force is needed to hold fractional charges together. No mathematical renormalization is required to hide infinite feedback loops. It is all just directional axes, geometric alignment, volumetric projection, and entropy taxes.
It replaces a physics of things with a physics of relationships.
I love that phrase.
It's true. In the Standard Model, an electron is a fundamental thing that mysteriously happens to possess mass and charge. In TDUFT, an electron is not a fundamental object. It is merely the label we assign to a specific geometric relationship, a perfectly aligned triad on the d-scored tier, casting a stable 3D shadow onto the d-cubed tier.
Wow.
A top quark isn't a completely different fundamental thing. It is simply a different geometric relationship, a highly unstable higher-tier configuration that cannot maintain a 3D volume, forces a 1D projection, and pays a massive entropy tax to exist for a fraction of a second. Everything is geometry.
It is incredibly elegant. It strips away the chaos. Let's take a breath and recap this incredible journey, because we have covered a staggering amount of ground today. We started with the idea of a 3D combination lock. Three simple directional dials: spin, polarity, and vibration.
Right.
By simply counting how many of those dials were aligned with a dimensional branch, we built the exact, strictly quantized fractional charges of electrons, quarks, and photons. The rule of thirds emerged naturally from the geometry of space.
From there, we examine the fundamental tension created by those locked dials and the dimensional imbalance between expansion and contraction, phi over ci psi. We discovered that this simple entropy ratio, when projected to a full 360-degree rotational cycle, perfectly derived the fine structure constant, alpha.
The magic number.
Yes, and when that exact same ratio was applied as a linear weight to the particle's alignment, it precisely calculated the anomalous magnetic wobble of the electron's spin to 6 decimal places, completely replacing thousands of Feynman diagrams.
Then we stepped off the charge tier and looked upward at the shadows cast onto the volume tier. We discovered that physical mass isn't a magical substance. It's a 3D geometric shadow-resisting movement through time. We saw how complex, resonating echoes of that primary shadow create the heavier muons and tosses using closed-loop matrices.
And finally, we witnessed the power of the universal unstable state mass law. We saw how a mathematically mandatory 10x dimensional projection minus a strictly calibrated entropy tax could flawlessly calculate the masses of the heaviest, most chaotic particles in the universe, the top quark, the W and Z bosons. It proved that their seemingly random weights are actually strict geometric inevitabilities.
We took the messy, fragmented spreadsheet of the modern standard model, we ran it through a 3D geometric prism, and what came out the other side was a highly structured, perfectly ordered lattice.
It is an incredibly empowering perspective for anyone trying to understand the universe. The underlying message of TDUFT is that reality is not a chaotic, impenetrable soup of fluctuating quantum fields that only a supercomputer can untangle.
Right.
It suggests that reality is highly structured, it is logical, the universe is speaking a language of pure geometry, and anyone can understand that language if they simply learn how to look at the correct tier of the ladder.
The D ladder. It really does change everything about how you visualize the physical space around you. But, as always on this show, I want to leave you, the listener, with a final, lingering question to ponder. A thought that goes beyond even the explicit math that Dukas laid out in this paper.
There is always a frontier to explore. The framework provides the rules, but we have only mapped a small neighborhood of the structure.
Exactly. We have spent this entire deep dive talking about the geometric shadows cast by the alignments we already know, the electron shadow, the quark shadow, the top quark resonance projection. But if all known matter, all known charge, and all known mass are truly just the resulting shadows of specific geometric alignments on this D ladder, wait, let me rephrase that without the pause. What happens if there are alignment sectors we haven't mapped yet?
Right.
What if the lattice goes wider than the standard model particles?
It's an incredibly intriguing premise. The geometry of the triad and the D-cubed volume operator doesn't technically place a hard cap on the existence of other configurations.
Right. So think about this. What if there is a specific combination on that 3-dial lock that casts a massive, dense, D-cubed shadow, meaning it generates enormous physical inertia and gravitational mass, but the specific triad alignment on the D-squared tier results in an n-aligned value of exactly 0.
Meaning it has no charge.
Exactly. Meaning it has absolutely no electrical charge, it cannot interact with photons, and it is completely invisible to the electromagnetic spectrum. Could the greatest overarching mystery of the cosmos, dark matter, simply be a massive geometric shadow sitting right there, just out of our dimensional sight, waiting for the right geometric lens to bring it into view? Is dark matter not some ghostly new particle, but just a different click on the D ladder?
That is a profound question to leave on, because if mass is just a geometric consequence of volumetric displacement, there's absolutely nothing in the physics forbidding the universe from casting deep shadows that we can feel gravitationally but cannot see electromagnetically. The underlying geometry allows for it entirely.
It makes you look at the empty space in your room completely differently. The empty air isn't empty. It's a rigid lattice of potential orientations, waiting to be aligned, casting shadows we haven't even learned how to perceive yet. Thank you so much for joining us on this deep dive into the trans-dimensional unified field theory. It has been a truly mind-bending trip.
A vital, paradigm-shifting exploration of what physical reality might actually be at its core.
Keep questioning the fundamental nature of your reality. And remember, the next time someone tells you the universe is just a messy, random collection of tuned parameters and infinite virtual ghosts, tell them to check the geometry. Tell them to look for the shatter. We'll catch you on the next deep dive.